Good morning, everybody. This is Mukherjee, working as associate professor in St. Peter's Engineering College. Today, I'm going to discuss about laser. Laser stands for light amplification by stimulated emission of radiation. Actually, it was not laser which was first developed. Maser was first developed. MASER, where Maser stands for microwave amplification by stimulated emission of radiation. Later on, laser comes into existence. So now what exactly a laser beam does? A device which produces a coherent beam of optical radiation using either stimulation of electronics, stimulation of ionics, or stimulation of molecular transitions from higher to lower states. This is going to produce energy radiation. We call it as stimulated emitted radiation. And that energy radiation, if it is sufficiently amplified, we get amplification of a stimulated emission of radiation, and if that corresponds to the required wavelength or frequency of our choice, we call them as light amplification by stimulated emission of radiation. Anyway, nowadays lasers are used in many fields like laser printers, laser pointers, laser surgery, laser missiles, laser communications. So laser has become an alternative for this technological development, especially in communication and other procedures. So basically, what are the properties of a laser light? The laser light is monochromatic. Mono, single, chromatic, color. Monochromatic, single color. We can produce single frequency, single wavelength light, unlike a normal white light or normal light. Lasers are highly directional. If we take a normal light, this light is divergent from 0 to 360 degrees. Any light is a divergent, but a laser light is a non-divergent, highly directional, like a scale. Laser light flows like a scale, and laser light is coherent. So here we need to understand what is coherent. Let us take a simple example. We have two sources of light. We have two different sources of light. These two different sources of light produced two different lights are called as non-coherent. Of a single light source is going to produce a light, and if that light is going to split up into two different light patterns or light wavelengths or light, we call them as coherent. So what is the difference between two different light sources and two light sources produced from a single light source? When you take two different light sources, the atomic excitation is different, the temperature of that atomic excitation is different, producing different properties of lights, which are called as non-coherent. But if we take a single light source, from which if two light sources are derived, these two light sources are derived from a single light source, henceforth having the same atomic excitation, same temperature, same wavelength, same frequency, except the angle and time. And we call them as coherent. So any two light sources produced from a single source will act like a coherent source. Any two different light sources will act as a non-coherent. And fortunately or unfortunately, laser is a coherent source. So lasers are monochromatic, highly directional, and coherent beam. Now, if we take the directional pattern, we have beam divergence. Anyway, we already discussed light is a divergent. So the beam, light beams, the divergence pattern is exactly given by theta d equals to beta lambda d, where beta is the factor of amplification distribution, lambda is the wavelength, and d is the beam diameter. And in lasers, the factor beta is approximately equal to 1. But in normal light sources, the beta is not equals to 1, producing a huge amount of divergence. That's the reason why being the value 1 for beta in this equation, theta d is almost equivalent to lambda by d, which implies that the light is going to travel in a straight like a scale. So now let us see the basic difference between incandescent and laser light. Incandescent, the left side, the light is produced and it is produced in all around 360 degrees. But in right side, laser is produced in single direction. So incandescent is a multi-directional, laser is a monodirectional or one direction or unidirectional. The light produced in incandescent is incoherent, the light produced in laser is a coherent. Incandescent, the light is multichromatic, whereas a laser is monochromatic. So that are the properties of laser. To achieve, to produce that kind of laser, the fundamentals required for producing laser are absorption, spontaneous emission, stimulated emission, and population inversion. These are the four things which are required to produce a laser. Absorption. When we give energy, atoms, they absorb energy and they move from ground state to the excited state. And we call this as absorption. After some time, the excited atoms will come down to the ground state. When they are coming to the ground state, they emit energy. We call it as spontaneous emission. But few atoms which are going to stay there in the excited state for a merely long period of time, we call that as a metastable state. And all the atoms after settling there in the metastable state will come down to the ground state at a time. We call that as a stimulated emission. But to achieve this stimulated emission, we need to satisfy one condition called as population inversion. Now, what is population inversion? The number of atoms in the metastable state should be greater than number of atoms in the ground state. When this stage is reached, all the atoms will come down to the ground state, producing a stimulated emission of radiation. And why the stimulated emission is a coherent? Let us see. So this is absorption, where energy is given. Atoms are moving from the ground state to the excited state. This is spontaneous emission. Atoms are moving from the excited state to the ground state, producing or releasing good amount of energy. But in stimulated, the atoms are coming down from the excited state to the ground state along with the incoming photon. So the energy released by the stimulated emission is having all the properties of the incoming photon. The incoming photon and the stimulated emitted photon, both of them are in same direction, same energy, and same wavelength. So these stimulated photons are always in phase with the incident photon, same wavelength with the incident photon, and travel in the same direction, producing or making this stimulated emission as a coherent source. And for population inversion, the number of atoms in the excited state should be greater than the number of atoms in the ground state. And that is not possible in normal atomic level. But this is achieved by the impurities. So this population inversion can be done or can be achieved only through the impurities. That's the reason why we are going to add impurities, and that impurities are going to move from excited state to the ground state, producing a huge amount of stimulated emitted radiation. But to achieve all these things, we need to have enough pumping where the number of atoms can move from ground state to metastable state to the ground state. And this is achieved by two different types of pumping schemes. One is optical, the other one is electrical. So in optical pumping, we'll be using flash lamps and high energy light sources. For electrical, we'll be using a potential difference, high energy or a very high energy potential difference across the laser medium. And in semiconductors, it is the electrons and holes through the junctions producing this pumping sequence. If you take a two-level system, energy is given, atoms are getting excited from level 1 to level 2. We call it as absorption spontaneous. The atoms are coming down from level 2 to level 1, releasing h amount of energy. We call it as spontaneous emission. but few atoms from level 2 to level 1 are coming down, releasing hν amount of energy, which is in parallel to the incident energy hν. We call that type of energy as stimulated emission. We have a small math to understand the stimulated emission. Let us take the Boltzmann's equations of the number of electrons in different states of energies. Let us take N1 as the number of electrons in energy E1, N2 be the number of electrons in energy E2, so that to achieve a population inversion, N2 should be greater than N1. And this N1, N2 are related by Boltzmann's conditions of N2 by N1 equals to exponential of minus of E2 minus E1 by kT, where K is Boltzmann constant at a particular temperature T. And to have this lasing action, we need to have different kinds of resonance cavities to produce the energies in the specified longitudinal modes. So now let us take our continuation of the earlier Boltzmann math. The probability of stimulated absorption is given by R12 equals to rho of mu into B of 12, where R12 stands for the probability of the number of atoms which are absorbing energy and moving from ground state to the excited state. Rho of mu is energy absorbed and B12 is the absorption coefficient. Similarly, we have probability of stimulated and spontaneous emission, which is represented by R21, where B21 is the stimulated emission coefficient with energy rho of mu. A21 is the absorption emission coefficient. Now, according to conservation of energy, absorption is always equals to emission. So N1 rho of mu B12 equals to N2 rho of mu B21 plus A21. Do simple math to produce rho of mu, the energy density, which is given by A21 by B21 divided by N1 B12 by N2 B21 minus 1. Now, according to Boltzmann statistics, N1 by N2 equals to exponential of E2 minus E1 by kT, which is nothing but exponential of hν by kT, where hν is the energy between two different energy levels E2 and E1. So substituting that, we are going to get rho of mu equals to A21 by B21 whole divided by B12 exponential of hν by kT by B21 minus 1. Now we are going to take the quantum principles of energy density, rho of mu given by 8 by hν cube by c cube divided by exponential of hν by kT minus 1. So equating the numerator part of both the equations, we get A21 by B21 equals to 8 by hν cube by c cube, which implies that the spontaneous absorption to the stimulated emission and spontaneous emission to the stimulated emission. So here A21 spontaneous emission and B21 stimulated emission. So the spontaneous emission to the stimulated emission equals to 8 by hν cube by c cube. Any system which satisfies the ratio of spontaneous emission to stimulated emission of 8 by hν cube by c cube can produce a beautiful lasing action, and any system which doesn't follow this A21 by B21 equation can't produce lasing action, and we call this relation as Einstein coefficients. A21 spontaneous emission coefficient, B21 stimulated emission coefficient. To achieve this, already we discussed population inversion is required, where the number of atoms in the excited state or metastable state should be greater than number of atoms in the ground state. And for achieving this, we require to have different types of pumping sequences. One is optical, the other one is electrical. So with this, I'm going to end this lecture of introduction to lasers. Please give your feedback. Thank you.